In this video, we solve problem 8.2.18-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says a genetic experiment involving peas yielded one sample of offspring consisting of 413 green peas and 178 yellow peas. We're asked to use a 0.05 significance level to test the claim that under the same circumstances, 24% of the offspring will be yellow. We're asked to identify the null hypothesis, the alternative hypothesis, the test statistic, p-value, the conclusion about the null hypothesis, and the final conclusion that addresses the original claim. We're asked to use the p-value method and the normal distribution as an approximation to the binomial distribution. So first it's asking, what are the null and alternative hypotheses? Well, in order to figure those out, I need to look at the original claim. So I look through the problem statement and I see we want to test the claim that under the same circumstances, 24% of the offspring will be yellow. So the proportion is that 24%. But we want that in decimal form. So we have p is equal to 0.24. If that's not true, we have p is not equal to 0.24. After writing down the claim and the statement that would be true if the claim isn't true, we look at these two. We say, which one does not contain the condition of equality? Well, that one's an equal sign, that one's a not equal sign. So this is the alternative hypothesis. The one with the equal sign is the null hypothesis. Now, typically I would just take this and I would rewrite it with an equal sign here, but I already actually have that up here. So the claim happens to be the null hypothesis this time. So let's go to MyLab Statistics and make sure that this is what they want. Okay, so we want a null of p equals 0.24, and an alternative hypothesis of p is not equal to 0.24. So it looks like option F is the one we're looking for. Great. And now they want us to find the test statistic. I'll share my paper with you so that we can compute the test statistic now. Now to find the test statistic, we need p hat, we need the population proportion that is assumed in our null hypothesis, we need the complement of that, and the sample size. Now, if you're wondering, where did this formula come from? Remember how hypothesis testing works. What we're doing is we're assuming that the null hypothesis is true. So we're assuming that p is equal to 0.24, and then we're looking at the sampling distribution of p hat. So if we had a bunch of samples that all had exactly the same size, and we computed a p hat, and we just kept taking samples and computing p hats, computing sample proportions over and over again, and then we looked at the distribution of those p hats. Well, if certain conditions are met, this sampling distribution of the p hats would be approximated well by a normal distribution. And we're told in the problem statement to do that. We're told that this normal distribution is an appropriate approximation to the binomial distribution, which means it's also an appropriate approximation to the sampling distribution of p hat. So we've got the sampling distribution of p hat here. Now, from what we studied back in lesson 6.3, the mean of the sampling distribution of p hat is equal to the true population proportion. That's what makes p hat an unbiased estimator of p. The expected value of p hat is exactly what we want it to be, p. But this time, when we draw this normal distribution, we're assuming that the null hypothesis is true. So we're assuming that p is equal to 0.24. And the question is, if the null hypothesis is true, is the value of p hat in our sample that's implied by this information significantly high or significantly low? We can determine that by finding the corresponding test statistic. first thing we need to do is compute p hat. So let's do that. P hat is the number of successes out of the total number of trials. And the definition of success in this case is the number of offspring that are yellow. So we have 178 yellow peas in our sample. And then in the denominator, we want to have the total number of peas. Well, we had 413 green peas and 178 yellow peas. So that's equal to this, 178 over 591. So our sample size is 591. And if I want to figure out what that is approximately, just so that I can compare it to that 0.24 in our null hypothesis, we've got this 178 divided by 591. Oops. That's approximately 0.30. 0.30118 says. Okay, so we're saying if the population proportion is actually 24%, if 24% of the offspring are yellow, so we would have a 24% yellow peas, is it significant to have a sample proportion of approximately 30.1%? So p hat is somewhere over here. So that's at 178 over the sample size 591. And that is approximately equal to that 30.01. In order to figure out whether that is significantly high or significantly low, we compute this test statistic. We're thinking of this as approximately equal to a non-standard normal distribution with a mean given by 0.24. So if I want the corresponding z-score, I take my continuous random variable p hat, I subtract the mean of the distribution of the p hats, and I divide by the standard deviation of the distribution of the p hats. Now, if we are assuming that the true population proportion is 0.24, this mean is equal to p, where p is equal to 0.24. So this p-value is the p-value in our null hypothesis. And then the standard deviation of this distribution, provided that the null hypothesis is true, is given by this formula in the denominator, the square root of p times q over n. So this is just going from this formula is just going from a non-standard normal distribution to a standard normal distribution. Now you're used to probably x minus the mean over the standard deviation. That's what we typically did when we were finding z-scores way back when we first learned about z-scores. That's exactly what we're doing here. We just have a p hat instead of an x. And the mean of that sampling distribution and the standard deviation of the sampling distribution, rather than the mean and standard deviation of some continuous random variable x. So that's what we're doing. And in practice, we evaluate this by evaluating this. So I have z equals p hat, or 178 over 591, minus p from our null hypothesis, which is 0.24. And then we divide by the square root of p times q. So we're assuming that the probability of success in one trial, or the probability of getting an offspring p that is yellow, is 24%. We write that in decimal form. And the complement of that, that's the probability of getting another color of p, is 1 minus the 24%, which is 76%, or in decimal form 0.76. And then we divide by the sample size, which in this case is at 413 plus the 178, which was 591. Okay, so that's our test statistic. That's the z-score corresponding to this p hat. So I think I'll do the denominator first. I want the square root of 0.24 times 0.76 divided by the sample size. And then I want to take the numerator and divide by that answer. So I'll type open parentheses 178 over 591 minus 0.24, close parentheses. That's the numerator divided by our last answer. And we get a z-score of approximately 3.4827. And they usually have us round that to 2 decimal places. So that's saying that that p-hat is 3.48 standard deviations above the mean. That is quite a few standard deviations above the mean. Normally, when we look at our standard normal distribution, we see about 3 standard deviations on either side of the mean. And this is just a half a standard deviation more than that approximately. Okay, so let's type that in over here on MyLab Statistics, 3.48. Great. And then we want the associated p-value. We can either use Excel to find the p-value, or we can use table A2. So I'm going to show you how to do both. Okay, so now I'm in Excel. And what I want is, for the p-value, remember, actually, let me look at my paper again, sorry about that. The p-value actually depends on the type of test that we're working on, the type of test, whether it's one-tailed or two-tailed or three-tailed. The p-value is related to this area beyond our test statistic. So if this is our sampling distribution of p-hat, we can use this formula to convert from this non-standard normal distribution to this standard normal distribution with a mean of 0. And we're saying, okay, if we're over here, and this is not to scale, but this z is, the test statistic z is 3.48 standard deviations above the mean. That's corresponding to this p-hat value over here. This area to the right of this is the same as the area to the right of the test statistic, because this is a non-standard normal distribution approximately, and this is a standard normal distribution approximately. Now, if it's a right-tailed test, that's going to be the area. But we have to look at the null and alternative hypotheses to determine what type of test we're dealing with. So I go to my alternative hypothesis. I see that it says not equal. So we don't care if our proportion is too high or too low. If it's not equal to 0.24, if we have evidence that suggests it's not equal to 0.24, we want to throw out the null hypothesis. Since this is a not equal to sign, this means, since we don't care if we're too high or too low, that means we're going to do a two-tailed test. In that case, the probability P is still the probability that we get a p-hat value like ours, or one or more extreme than that, so it's a value out in this tail. But we don't care if it's on the right or on the left. So we want a p-hat value that is as extreme as that. So it would be the same thing, but well, it should be symmetric. It should be that same distance away from the mean on this side. It's as extreme as that, or more extreme. So to the left of that. The same thing here. If I've got a z-test of 3.48, I'm looking for test statistics that are greater than 3.48. I want to know what's the probability of that. And I also want to know what is the probability of getting a test statistic that is less than z equals negative 3.48. It's that over there, because we don't care if we're off by being too high or too low whenever we're doing a two-tailed test. If our p-hat value is in this region or this region, or excuse me, if our test statistic is in either the left tail or the right tail, if we looked at that critical region using the critical value method, either one of those would be fine to allow us to reject the null. But with the p-value method, we're looking for the probability that our p-hat is as extreme as ours or more extreme than ours. And with a two-tailed test, we're talking about on the left or on the right. So that's this area times, or this area plus this area, which is the same as this area over here times 2. So this will be 2 times the probability that z is greater than, 3.48, or 2 times whatever we get when we type 3.48 into Excel. But that is an area to the right. I really need an area to the left. So one way of doing that would be to compute 1 minus the probability that z is less than 3.48. That would give us the area to the right. That's one way of doing it. You could also say, well, that area is equal to that area. So let's just find the probability that z is less than negative 3.48 and then double that. It's going to give you the same answer either way. We haven't talked about that one too much, so let's just do this one. So I will find the probability that z is less than 3.48 using Excel, and then I'll subtract it from 1, and then I'll double it. Okay, so we say equals. If I'm in Excel, I'm trying to find the probability that z is less than 3.48. So I want normal distribution, norm.dist, open parentheses. My z is 3.48. The mean of a standard normal distribution is 0, standard deviation is 1, and we do want the cumulative area to the left, so we say true. And that is the area to the left of 3.48. We actually want the area to the right of that, so we'll take 1 minus that answer to get the area to the right, and then we want to double it. So I want 2 times that answer that I just found. So I get a p-value of approximately 0.0005 using Excel. So that's one way of doing it. Now, another way of doing this is to use table A2. So let's go to table A2 now. So I still want p equal to 2 times 1 minus the probability that z is less than 3.48. So I need to go to my positive z-scores table, and I'm finding the probability that z is less than 3.48 by going to the page of positive z-scores and looking for 3.48 here. Well, here's 3.4. This is 3.40, 3.41, 3.42, 3.43, 3.44, 3.45, 3.46, 3.47, 3.48. So you get that right there, 0.997 as the area to the left of z equals 3.48. Okay, so then when I subtract those, I get 2 times 0.00003, and I get approximately 0.0006. That's using table A2. So you see that when we use Excel, we get 0.0005, and using table A2, it's just a little bit different, but it's pretty close. So let's go back to our homework and show that both of these are acceptable. I guess we have to choose one for the homework, don't we? So it wants a p-value rounded to 4 decimal places. So we'll say 0.000. And let's use the answer from Excel, 5. All right, MyLab Statistics likes it. And then we want a conclusion about the null hypothesis. So we're taking our p-value, which is this 0.0005 or 0.00006, and we're comparing it to alpha. And alpha, let's see, was in the original problem statement as a 0.05 significance level, or you can see on MyLab Statistics, it's right there, it's at 0.05 significance level. So alpha is 0.05. And that's clearly more than 0.0005. So P is less than or equal to alpha. That means the probability of getting a p-hat value as extreme as ours or more extreme is about 0.05%. It's a very small probability. Now that probability came from assuming that the null hypothesis is true. So we say that if under an assumption, something is supposed to be very improbable, but then it happens. If it's happening a lot more often than we might expect, we might say, our assumption must be wrong. There must be something wrong with that assumption. So we're going to throw out our initial assumption, which is that the null hypothesis is true, because P, that probability is so small. This is the rare event rule again, guys. But the underlying assumption here is the null hypothesis. So we're going to reject the null hypothesis because P is less than or equal to alpha. So we say reject the null hypothesis because P is less than or equal to alpha. Great. And then the next part asks for our final conclusion. Deciding what to do with this regarding our final conclusion involves looking at the claim itself and the alternative hypothesis. So we're rejecting the null hypothesis. And the null hypothesis is the claim. So we're rejecting the claim. So we're saying we have sufficient sample evidence to reject the claim that the true population proportion is 0.24, or alternatively, there is sufficient sample evidence to warrant rejection of the claim that 24% of the offspring will be yellow. So we say there is sufficient evidence to warrant rejection of the claim. Oh, that's B. Okay, that's it. And that's how we do that one.